Which ion cannot catalyse the reaction between iodide and peroxidized sulfate? So let's have a look where iodide is here. It's been made in this reaction with an electrode potential of plus 0.54. So if it was a reactant reacting, it would start here and make iodine and 2E minus. And so if it were here going in the other direction, it would be minus 0.54. My peroxidized sulfate is going in the right direction. Here it is as a reactant, making 2SO4, 2 minuses. That's plus 201. So I'm going to add these two together, plus 201 minus 0.54. So the electrode potential for this reaction between the two is plus 201 minus 0.54 plus 1.47. Now I've got another ion which is going to catalyse it. Let's have a look at the possibilities. When I look at the reaction and add on the electrode potential for this ion, when I add it to plus 0.47, it needs to leave a positive value overall if the reaction is going to go ahead. So CO2 plus, where's CO2 plus? It's here. It's being made in this reaction. So if it's going to be a reactant, it needs to go in the other direction. And in the other direction, it's minus 1.82. Minus 1.82 plus 1.47 would give an electrode potential of a minus value, minus 0.35. So that one wouldn't go ahead. So the answer is A. Let me just check Cr2 plus. Cr2 plus is here. Cr2 plus is a minus value, but going in the other direction, if it's a reactant going in the other direction, it's going to be plus 0.41. 1.47 plus 0.41 is 1.88, so that would go ahead. It's a positive value. Fe2 plus, it's here, so going in the other direction, Fe2 plus going in the other direction, being a reactant here and forming Fe3 plus, it would be minus 0.77. So minus 0.77 add 1.47 is going to give a positive value of 0.7. And finally, Fe3 plus going in this direction is plus 0.77. Add 1.47 would give an answer of 2.34. So my answer is A. Which species has a shape influenced by the presence of one or more lone pairs of electrons around the central atom? So let's have a look which one of these have got lone pairs. Al is in group 3, so it's got 3 electrons in its outer shell, 3 Cl's bonding with 3 covalent bonds, each of those 3 electrons, one each, for each of the Cl's in a covalent bond. That's going to have no lone pairs left over. ClF3, well, Cl's in group 7, 3 F's bond to 3 of those electrons in 3 covalent bonds. That will leave 4 electrons left over. It'll have 2 lone pairs. Those 2 lone pairs will go one up and one down at 180 apart, and will leave 3 bonding pairs in a trigonal planar shape with a bond angle of 120. So that's influencing the shape. That's got lone pairs. Let's check the others out though. I is in group 7 plus lost an electron, so now got 6 electrons, got 6 F's bonding each of those 6 electrons each in 6 covalent bonds, so that will have no lone pairs. P is in group 5, gained an electron, so it's now got 6 electrons, 6 Cl's, each bonding with 6 covalent bonds. Each of those 6 electrons got no lone pairs left over. So my answer is B. Solutions were mixed using equal volumes of each solution. Which pairs of solutions would give the greatest mass of solid? Well, in this one I'm going to get barium chloride and magnesium hydroxide, barium sulfate and magnesium hydroxide, barium chloride and sodium hydroxide, and barium sulfate and sodium hydroxide. Well, for a start, barium chloride is soluble, magnesium hydroxide is insoluble, so I'm getting one soluble and one insoluble product. Here I'm getting barium sulfate, which is a white solid used in barium meals. Magnesium hydroxide is insoluble, so I'm getting barium sulfate insoluble, magnesium hydroxide insoluble. I'm getting 2 insoluble products. Sodium hydroxide is soluble, barium chloride is soluble as well, so I'm getting two soluble products here, and I'm getting barium sulfate, which is insoluble. I'm getting sodium hydroxide, which is soluble. So there's only B that gives two insoluble products. Which indicator should be used in a titration to find the concentration of a solution of methylamine using 0.01 mole decimeter hydrochloric acid? Well, 0.01, if I do minus log to the base, this is a strong acid, so I'm getting 0.01 hydrochloric acid. It completely dissociates into its ions, so it's going to make 0.01 H pluses. If I minus log to the base 10 of that, that's pH 2. So pH 2, and the shape of my curve is that it will start with pH 2 and then it will rise, it will go, and then it will rise very sharply from pH 2 upwards and then start to tail off, because this is a weak alkali, a weak base. So I'm looking at something like pH 2 up to maybe something like pH 7, pH 8 before it starts to tail off then and slowly increase up to probably about pH 10. So I've got a shape of a curve that's going flat and then up and then tailing off slowly for a strong acid and a weak base, and it's starting off at pH 2. So this is not in the right range. These are not in the right range. It's pH 3 to pH 4.6 where I'm getting an equivalence point, where I'm getting an end point where the pH is rising quickly. So my answer is B.